the talks are not going to be about blockchain. Sorry if anyone comes to hear specifically about the subject, right? But obviously questions after the talk. It's a very broad topic, as Domen was saying in the beginning. And the talks are very technical in a way, which is the type of talks that we tend to host. That's it. I'll leave you guys with Domen, and
thanks.
You can take
Can you hear me well? Is this supposed to echo, or? Oh, is it just for the stream? Okay, good. All right. I'm really glad I'm here. Before I start, I just want to, if you have any questions, please, interrupt me, because I have short memory, so I'll forget. And yeah, if I forget to clarify something, or if something is unclear, please let me know, because I want, everyone to be on the same page. Just before we begin, I would like to know who is using, a purely functional programming language in their job. Is there? There's 3 hands. Okay. Purely functional programming language in their job. Okay. That's, a good start. Yeah. Okay. Elm is one of them. Yeah. What about functional language like Scala or something? No, that. Okay. Good. Yeah, so I won't talk about the blockchain, but I'll talk about one of the things we do in IOHK, which is, build software and deploy it, which, in any company, that's kind of like part of the process. So just a brief inspiration. Oh, it should be centered anyway. A brief inspiration, for those who are a bit unclear about a purely functional languages. The idea is the following: we have functions, and we want to say, for example, a function accepts an integer, returns an integer, and we want to say in the type signature, accepts an integer and returns an integer, and we want that function to do exactly that, right? So if it logs or if it accesses a database, the type signature doesn't say that, so it shouldn't do that, right? So that's the nice beach around where we have these pure functions, and you can put stuff in, you get out, and you can test them easily, and everything is great, and developers are happy. But then we also have this code that's kind of like trying to interact with the world, because a program without inputs is usually boring, right? It doesn't do much, or for most of things we do. And we want to make that code kind of like compact at one place, right? And this is where the monads come in and the other abstractions, and we want to kind of like sort it out. And ideally, we want to keep this part like as small as possible, right? We start with a project, and there's a lot of developers. We're in the rush, and we have to make it, and we keep this kind of like messy. But when we try to put it all together and say, this is the ugly part of the code, but we know exactly where it is, right? We don't want to leave it all around the place, so it's hard to reason about. So that's kind of like the inspiration around this. So Nix itself is a language that was designed for one very specific problem. So we call those languages domain-specific languages, and they're not fully fledged like Haskell or Elixir or Scala, but they're just for that particular area. So what area is Nix solving is packaging. How do we package things, right? And what's the problem? So if you think about your favorite build tool, be it Makefile or I don't know, in Python, setup tools, or whatever you think about it, or your Linux distribution that comes like with apt or something. If you invoke like a build process, you get some files out, right? That's your package, compiled package or whatever, and you put that into your file system. Now the problem is packages have dependencies, so you take another package, and it takes this file system kind of as an input, and then builds another package and so on. So you're kind of like have this stateful loop. The problem is this loop, nobody really understands, the big picture after you build 500 packages, right? Or if somebody goes and changes something and adds another package, it's really hard to reason about. You know, that's why we kind of come to two solutions in industry. One is the containers, where you say build something from scratch, and then you know that this is exactly how you come from zero to something. And the other approach is Nix way, which is you try to control, you try to eliminate this state loop, and that's what Nix does. It basically eliminates it, so that you can reason about dependencies and state also when you package things. All right, so this is a bit very abstract and inspiration. So let me get into specifics. So it's, as I said, it's a DSL. That's a bunch of buzzwords, but let me try to explain. It's a DSL. As I said, it's meant only to solve the packaging problem. It's purely functional, the previous slide. It's dynamically typed, so it's not like Haskell, and you can have dynamically typed purely functional languages, actually. And I'll show you later with examples what it means. And you can think about Nix as kind of like a JSON with functions. You know, that's basically what you want to think about, with a twist of lazy evaluation. And for those that know Haskell, it is the way to. Most languages are eager evaluated. That means, you know, as soon as you do something, it will already go into memory, and it will, you know, either throw an exception or, you know, eventually be an integer somewhere in there. Whereas in Nix, that's not true. I won't explain too much about this, but it's not that important really. And you know, there is a lot of history about Nix, but it kind of started with 2004 imposing a memory management discipline on software deployment. I will explain how Nix is eventually like allocating memory automatically and reference counting. That's, you know, how most of languages nowadays work, the high-level languages. And then in 2006, Jelko Dostro wrote the PhD, which is a really nice read. I recommend it. People don't usually read PhDs, but there is very little math, and you can skip those few sections, and the rest is like explaining why, you know, why this design is needed, and basically my intro in a more precise way. Any questions so far? Right. All right. So, you know, Hello World is something like this. Since it's a package manager, there is kind of like this, you know, chicken and egg problem. You have to install it somehow. So we have this script that you can run, and this works on Darwin and Linux. So even if you have an Apple, you can start playing with it. And then you can install the REPL, and you know, 1 + 1 is 2. So, you know, I want to give you just a brief feeling about the language, so you know what I'm talking about. So, as I said, you know, it's pretty functional. Everything is about functions, but it's dynamically typed. You see, I don't declare any types, but it's, you know, strongly, you know, it's not JavaScript, right? It will not try to guess things for you. So if you do like, if you use operators on wrong types, it will still tell you that you're doing something wrong. And you can get like the types of values and so on. One of the special things it has, if you use this double single quote syntax, it will basically strip off all the prefix, all the white space that's before the first character anywhere in your kind of source code. So the idea is that you can indent your configuration files, but it will strip them. So you can like yeah. So if it's a double quote, it's just a normal string. If it's 2 single quotes, then it's this thing. So this is something that's a bit something to get used to. Then it has this kind of like a sea of functions that are built-ins, and you can see all of them if you say built-ins. And these are the functions that, you know, operate on the basic values. And as I said, think about like JSON. I won't go into all the types, but there's nothing fancy in there. And you know, as I said, it's JSON with functions. So you have functions which you declare them with kind of similar than in Haskell. And then you apply them by just, you know, white space 3. This is a function call, and it passes 3 as an A, and then, you know, it multiplies. And yeah, then that's pretty much it. It has integers. All right, so lazy evaluation. I want to show you how this, you know, in practice, what you can do, for example, if we have file A that has an attribute set, you know, you can think about this as a hash map or dictionary, whatever is your preference. And you say, oh, A is 3, but I get B from actually file B, but then you define file B and say B is 4, but I get A thing from file A, right? So it's kind of like those two files reference each other. Then you can actually get, you know, if you evaluate any of those, you will get the right thing back. And that's kind of like where, for example, a lazy language works better than an eager one because you would get a cycle, right? Just an example. So all clear so far, right? So okay, now we have this language, right? So what does it have to do with packaging? And let me try to explain this, you know, step by step. So it's a two-step process, right? First is we have this language, and we call Nix instantiate you know, command line tool, which goes from Nix expressions to derivation, and then we call Nix store -r. Again, Nix is not really famous for having good command line arguments architecture, but this is being reworked because this is actually as it was designed for the PhD in 2006. So if you call Nix store -r, then you go from a derivation. You would see here at the back, this file is the previous one .drv, and this will get out to you a build product. And then this build product is essentially a folder with files, or it can be a file itself. So again, Nix instantiate goes from expressions to a derivation. Nix store -e goes from derivation to build product. The reason why it's two-phase is because you want to, you know, we don't say compile, but we say evaluate. Nix expressions to derivations is to get, you know, your basically packages, and then you can copy them to another machine, and then you build them there, right? So the idea is to support, basically you can parallelize that across multiple machines and so on. That's why this is split into two phases. And there is Nix build command line, which is kind of like basically those two things together. And usually you don't go you don't do this explicitly. If you do it, it's usually some tools that wrap up and distribute this and then build and collect the results. Okay, so this is like very briefly the phases, but now let's go into each phase a bit more to show you. All right, so you know, Nix expressions. So as I said, language is boring by itself. The main function that actually does all the heavy lifting is called derivation, and you pass a bunch of arguments, and that's basically how you build your package. Now this is the most simple package you can ever do. And it basically requires 3 arguments. You know, what's the name of the package, what system is this for, and how to build it. And builder is basically an executable. It can be a bash script, it can be, you know, whatever. In this case, we take a compiled file by GCC, and we just, yeah, we have a derivation. Now, how do we create this touch? You know, let's create a very simple C program. It doesn't really matter what's in there. It's basically just basically what it does. It takes this out environment variable and it creates it, and that's it. So that's the only requirement in Nix, is to create this out directory, and this out directory is actually this path. So you have the builder itself has to create this folder. That's the only requirement. So that's how we create this touch executable. And so the question is, you know, well, it's a language to build stuff. So why doesn't it build, you know, with with GCC and compiles it? So the problem is, if you look at the first snippet, you know, you have to get GCC from somewhere, right? So this is like a bootstrapping problem. Like, how do you compile something if you have nothing, right? So what Nix does, it provides Nix packages where you have something called standard environment, and then you have make derivation, and this provides you with like the basic setup of what you would expect to build something, and that's like, you know, GCC and all the core util tools like sed and make and so on. And then you can actually tell it like this: how does it find the source, and how does it, you know, compile? And that's actually what you use in practice. Nobody uses derivation really, because that's like very low level. All right. Any questions so far? So, just to go briefly back. So now we instantiate this derivation that we have in this empty file, which creates this. Basically, what it does, it will just create a directory, and we get the derivation as a result. And this derivation is, it's not clear here because it's like a long one line, but it's like a very special, very simple intermediate format that Nix uses. You don't ever modify it or anything. You just have it there. And again, you copy this somewhere and then you build it with Nix store -r. And in this case, this builder, as I said, not everything it did, it was just creating this file, and that's it. That's the most minimum package you can do. Any questions? Right. So, okay, now we can create packages, right? And okay, how does that make like a file system then? How do you create an operating system out of this, right? So the idea is that that these inputs here are the inputs to our purely functional language, and this is where purity in Nix comes from. So this package only depends on these things here, right? These inputs here are pretty boring, but imagine you would specify dependencies here and so on and so on. So the idea is that it doesn't go into your file system randomly, but it takes these attribute sets, passes them to a builder, and then builder executes that in a sandbox environment. And that makes sure that only with these attributes here you can achieve this result, right? And I will explain the sandboxing later. So then how do you create sets of this is something called profiles. So for example, if we have Firefox at the bottom, you see that Firefox binary depends on the user environment Firefox binary, and that depends on other libraries and so on. And then link together into a profile, and you can see in the second column, this is like a history. So every time you add something, a new symlink is created, which is like a new version. And then if you look at user directories, each user can have different packages, and their Nix profile points to one of these profiles, which points to all the packages. So it's kind of like a symlink farm. And why symlinks and why complicate all of this is because Nix support rollbacks, and a symlink is an atomic operation in Linux. And if you shut down your computer in middle of symlink, it will either happen or not. It's one of the rare operations. Moving a directory and symlinking are the two operations that are actually atomic. So the idea is, by switching this symlink from one version to another, you basically make sure that you can roll back or move forward without worrying if something goes wrong. So let's say I deploy to, I'm in a very crappy connection, and I deploy something, either it will finish completely or not, right? That's the idea. And moreover, I have the whole history, so I can go back. So the way it works is, it will keep, when you build new packages, none of them will get removed from this Nix store. They will just accumulate, and then you have a separate process which is called garbage collection. Again, I'm saying that this is similar to memory management in high-level languages, which will then collect, and you can say, keep me a history of 5 revisions per each user, and that's what I want to have on my system. So yeah, this is how profiles work. Any questions? Yes, yeah, garbage collection is then a process, and it supports things like you can tell it garbage collect I don't know 1 gigabyte, or you can say garbage collect everything that's older than 30 days, or you can say garbage collect and leave me 5 versions of history. There's different ways to look at this. And for example, on our CI servers, we keep every time just like 50 gigabytes, and the rest should be there because we want to keep as maximum as possible of history so you can choose your strategy basically. Any other questions? All right. So as I've said, yeah, this hash is basically, you know, a hash of all the inputs that you pass to derivation, and then this is all running in a sandbox. So what does that mean? It uses chains root, so completely, you know, it separates the file system, it separates the networking, it separates everything. It's basically kind of like a Docker environment, and then it uses those inputs, and if there is a package in that input, it will build that first, and so on, you know, up to the top, and then it will build that until it comes to your package, pass all those packages as an input, and build that in isolated way. Moreover, it will also disable the networking, so you're not allowed to access the networking, because if you would, then it wouldn't be pure, right? You're depending on attributes to your derivation, but you're depending also on the internet, which can be anything, you know. So then the question is, how do you even fetch, you know, source and so on? And there is special derivation called fixed output, and fixed output derivations, basically what they mean is they have a predefined hash. So when you do want to access the networking, the internet, you have to specify what's the hash of things you're getting back. So again, we're making sure that the inputs are fixed up front in the Nix language. So in this case, we say, you know, fetch me something, and this should be the expected hash. Okay, so as I said, the way to think about this, it's like memory management. Their functions, write text is like a wrapper around derivation, just to make it very easy to create files. And it accepts two inputs. One is the name of the file, and the second one is the contents. So basically, if you say write text foo.txt, you get, you know, you get back this. It doesn't. Right, it's broken. Okay, so you get back a file in the Nix store, which will be which will have contents bar. So the idea is you just get that. You know, you don't tell it how does it do it. You don't tell it anything. You just say I want that, and provide me that, and write this in. And you know, it also supports of course substitutions. So it's kind of like a, you know, configuration templating language as well, as you think about it. And what's interesting is if you look at dependency tree now of this last line, this actually depends on the bus, which is another derivation, right? So Nix, this way it knows what are the dependencies. As soon as you reference a variable, that means it depends on that thing, right? So the way it figures dependencies is basically you just use the thing, and then it knows if you have referenced something that this is a dependency. So I hope that's clear. And this is basically how it figures out the whole tree, what it needs to build. So again, like you're just using essentially variables, and you're creating graphs of dependencies. So now to the second part of the talk is, you know, is it used in industry? Was it PhD? So it's probably useless, right? That's what people usually think in stereotype way. But actually, Nix is used quite widely. You know, we've been using it in IOHK with, you know, it was I think right now it's not because the whole market crashed, but it was the fifth cryptocurrency in the world by the market capitalization, and we use it for deploying things and so on. And it's used by other companies, mostly in the Haskell industry right now, because, well, we can go into debates because of why, but it's mostly because Haskell people more believe into properly designed things, so they want to have very precise control about how they build their software as well. So, you know, how do we use it? Just briefly, we use Haskell everywhere as well, together with Nix. And there is a tool called Cabal to Nix, which takes these, you know, Cabal files, which is how you specify how to package a Haskell thing, and it basically automatically generates a Nix file. You know, you can see at the top, these are all the dependencies as a function. You get them as inputs, and then you basically call this make derivation with all, you know, this is all auto-generated, parsed from the metadata, and it figures out if it's a library or not, what are dependencies, you know, what does the tests need, so on. And then one of the nice things about Nix is that it's hackable. It has an API. I've been always deploying software was always my passion, and one of the major things I always miss is able to tweak something, right? You take, for example, Docker images, but you can't really compose them. You can't just join them together. It's kind of hard, right? And here, what you can do is you take this derivation, and then you can override one attribute, and you just tweak, essentially how you will build it with just key values. This is so for Haskell we have combinators. This is like a very common term in the functional programming. But what it means is you can pass it all. It's a group of functions that you always accept the same type of inputs. In our case, derivation, and they will kind of like modify it. So, for example, I can take Alex and say enable this flag, and it will return me a new derivation, but with this flag on. And then I can say don't run test, and it will again return a new derivation which won't run test. So I can create multiple versions of them, and basically I could build a matrix of the same package one time with these parameters, the second time with this, and so on. So I could do all this kind of stuff. So this is one of the where Nix then starts to shine in for example, to give you a concrete example, we build, for example, many different kind of Docker images. We built some software with debugging on, with profiling, and so on. And we basically have functions like just this that say, oh, enable profiling, and we build 2 versions, for example. You can also build Docker images without Docker itself. For example, we built Cardano Docker images for different environments. And it's again, behind this is a derivation, but this is more like a high-level function where you pass it, what are the packages that end up in the Docker image, what to run, and what things to expose, and so on. No. No, you don't need root to run Nix. No, you don't need root. Yeah. So it doesn't need Docker at all to build this, and it takes like almost no time to build it. So that's way quicker than the Docker itself. So again, one of the nice things is you can take this and tweak this, and we have different environments, and we just build. And one of the cool things is we statically compile Cardano, so the Docker image is like 30 megabytes, just executable. That's it, nothing else. We ship this to exchanges and so on. So now this is kind of like just and then this is how you build it, and then you load that in, and then you create a volume for the state, and then that's based. I mean, this is just Docker. This is nothing to do with Nix itself, except the first line which builds that thing. So yeah, just what you can do with all of this. There is a whole spectrum. Nix replaces the whole stack of tools. There is NixOS, which is an operating system where you declare how you want your operating system to be, and you take this file, you put it on computer, you say execute this, and it will get you exactly this kind of operating system. So we are using that. So there is also NixOS tests where you can spawn multiple virtual machines, and they interact with each other, do kind of things, collect results, and report that. You can build Docker images, as I've showed you. We are building, a lot of Haskell software with this. We have deployments with Nix hubs, which is kind of like Terraform, if you know about it. You can deploy to Amazon, and we use this, for example, to launch a benchmark and spawn like 100 machines and benchmark our blockchain software to see what's the throughput of transactions and things like that. And we have written tools like Stack to Nix, which is Stack is a tool that builds software for developers. It's kind of like a development tool to work on Haskell packages. But we wanted to map that specification of Stack to Nix. So we want to have developers using the same versions as we do in production. So we wrote this Haskell program that basically bridges the two. So you can make sure that developers use the same versions as then for production, and this automatically generates Nix expressions. It's like a huge file, 2 megabytes of all the dependencies we use. Right. So I think that's it. I can, if you have questions, I can answer those, or I can show you around a bit. Everything we do in IOHK is open source, so I have the luxury to show you all of it, browsing through that. So, but first, questions. Yeah, there is Python. There is a lot of languages supported. Python is I was previously a Python developer. Python is very tricky because it's very hard to package stuff in Python because of the tools Python has are very old and not ideal, but it's doable. We have a couple of people doing that, and we have a lot of scientific things packaged with Nix and so on. For example, most Python people know Conda. Conda was actually inspires from Nix a lot of things. Actually, I talked to the guy that worked there who engineered Conda, and actually they took Nix and rewrote it in Python, essentially. Just because Nix didn't support Windows, they didn't know C++, which is what Nix is written in. So they've decided it's easier to re-implement the whole thing in Python. Beats me, but sorry? No, Nix was developed is written in C++. Yeah, it's the first version of Nix. Yeah. Yeah. We're one of the biggest GitHub projects. We are just having a release by the end of this month, and I think we reached 2,000 pull requests per month. So it's crazy. We are building a lot of automation around that because it's really hard to handle that. It's one of the challenges that we have. Yeah. No, so Docker has a specification. How do you? It's basically just a layers of tar files. So we reverse engineered that and wrote our tool that basically skips all the crazy Docker stuff and just creates a tar with all those layers with Nix. I mean, not me. One of the Nix guys. Yeah. Right. It uses unshare. It uses the unshare. I don't know if you're familiar. I think that it's basically kernel namespacing feature, which is used by Docker as well. Yeah, very similar. Yeah. Yeah, so each package basically goes into a sandbox, and Nix tells it what it should have available, and that way we know it's reproducible, right? Which is the key aspect. Actually, we measured this. I can find the issue. It's something like, let me remember. For 100 packages, the overhead is like 2 seconds or something like this. Oh, in terms of space. Right. That's hard to measure. Because because you're just adding stuff when you build. The Nix store gets quite big. Like I think mine is like 500 gigabytes. But this is my day job, so I build things all the time. But yeah, it can get quite big because of that. Yeah. We also have a thing called multiple outputs derivation, where you can split your resulting package into multiple Nix store folders. So for example, in Haskell, we split documentation and so on. So when we build things for production, we don't include a documentation or things like that, and that reduces the whole closure, which is what we call the whole dependency graph. So it's smaller. Yeah. Any other questions? Yeah. So this is I should be more precise. this is statically in terms of Haskell, but it still has a couple of libraries that are system libraries as dependencies, so glibc and so on. You could use Muscle as a glibc alternative, and we have a guy that's actually working on that. I'm actually the DevOps lead, and we hired a guy to cross-compile with Nix from Linux to Windows Haskell, and that will be done in the next month. And you can statically compile as well, but it's a bit harder to do, and we just haven't done it because there is very little benefit in our case, because it's like going from 30 megabytes to 20 megabytes of closure size or something. It's a big improvement, but yeah, it's not. There's other things we have to fix before that. Yeah. I don't know. I mean, I can show you around. I don't know how much time I have left really before Alex kicks in. Not much. Maybe I can show you around a bit just to give you, let's see. Okay. That never works, right? Well, I don't know if I have internet right now, but let's see. I don't think I have. Oh, this will probably fail. Right, so now it's compiling because the internet is down. So let me show you rather, for example, you can query, let's say I want a dependency graph of ls, right? I can say give me the path to ls and then give me the dependency tree, and I get a dependency tree of that. And if you look at the dynamic libraries of that, you will see that all the dynamic libraries point to the Nix store, right? So when it's all built, it's all comes very specifically from those packages. So you can have multiple glibc versions on your system and so on. One of the things Nix support is a lot of different versions one by another. Unfortunately, I should have configured my Wi-Fi. Maybe let me do this very quickly. No, that was the wrong one. Yeah, this is NixOS, yes. I want to show you Nix, how we, for example, configure our deployments. If this works. Is it BRPX? I have to spell things. Yeah, E820. Okay. Next try. All right. All right. So now, if I go to let's see if this gets the. Oh, it's building. Right. So here you can see, for example, that if I build, if I build the node, then it depends on all of our other packages. And one of the really cool things about Nix is that, there used to be this source versus binary Linux distribution debate, right? And the way that Nix works is this hash, as it uniquely identifies all the inputs, you can either say, oh, I already have this package for this hash, or I don't, and I have to build it. So if you let's say I make a change in Cardano cell delegation package, right? Then this hash will change of that package and all of them that depend upon it, but none of the others, right? So when I build something, it will automatically reuse the others, but build all the reverse dependencies, right? So it's very granular, right? So this is really nice for CI, for example, where you don't have to build everything over and over again. What's even better, usually, a CI continuous integration solve that by creating a cache, but we all know that caching is you always go for a cache when nothing else works, and then you kind of sin every time the cache breaks and so on. Caching is evil, right? And here actually you know that for every time you build that, you will get the same package. So maybe I show you our repo. We also specify deployments in X. I don't know. Let's take something really, really interesting. Not that one. Maybe Cardano Explorer. Right. So, for example, this deploys our report server, which is kind of like error collection. And at the top, you see we define different options, what you can actually set for this service, and then here we for example configure the EC2. How does it what security groups does it get on Amazon and things like that. This for example says give the instance 200 gigabytes of disk space. Then we create. This specifies how the user is created. This specifies how it runs the actual Haskell executable. So up down here, I should make this bigger probably, right? So yeah, it like executes Cardano report server and passes parameters, and this is like a service, and then we can set the Zendesk parameters. So this is like a module that specifies how to deploy this specific service. And actually, back then, if you're interested, I wrote this. Maybe it's still a good source. I don't know. I never know how to Google it. Yeah, there you go. Why Puppet, Chef, Ansible aren't good enough, and we can do better. I wrote this, I think in 2014, yeah, which explains this declarative configuration of operating systems and how actually these tools that we have today are very stateful, right? Ansible goes and it checks. Does the user exist? No. Okay, then create it. Oh, you want a user with this group. Okay, let's see what the user is. Let's see the groups. So this is very stateful. It's really hard to program it right. You always know that when you program things and you have this state here and this here and you have to kind of match the two, it's really hard to make that work. And Nix doesn't do that. It's all about this referencing other Nix variables and then deploying that. And Nix by design will make sure that this is done as it is, not by comparing anything, right? So it's a functional language that results. You can imagine that an operating system is like a result of the whole program, right? And it doesn't inspect any state. Yes. You can pass it's functions, right? So you have inputs and you can pass it arguments. And for example, I had this other talk, but I don't want to steal Alex's time as well. Let me just show you this quickly. This was another project I did, but it demonstrates nicely what can be done with this tooling. So Snap is a software that does very high-speed networking up to 100 gigabyte, which Linux kernel doesn't handle. And while developing these networking drivers, the guys had a challenge: how do you test all kind of stuff, right? So they wanted to test, different versions of QEMU, like all the releases. They wanted to test, different glibc and muscle. They wanted to test different hardware. So all of this, right? So with Nix, I created these packages to execute a benchmark, and then, a QEMU was a dependency, and all of these things were just a function input. How do you build that benchmark? And then I basically took all of this and created just a huge matrix of them, and built all of these benchmarks, and then generated a huge report where you see that, where it basically compared all of these things relatively, and you can see if, for example, a new version of QEMU comes out, you can see on your report that it was QEMU's fault, not ours, right? That this broke. So this is kind of like the fine tuning you can do then by specifying all these inputs to the. I can maybe show you the report, but just to have an idea. If I only knew where it is. All right, let's see. This is slow. Any questions meanwhile? Maybe Alex, you can, yeah. Okay. Let's see. So this is the CI tool that this is failing now. It's supported. This is the CI tool that's built for Nix, and it basically builds the whole dependency tree. There you go. So, this is like, for example, this takes Snap software and it compares 3 different branches, right? So it uses the same Nix expressions, it only points to a different branch, and then it graphs this. And then, you have a lot of benchmarks for different kind of software parts. And here you can see, these are, for example, as you said, as you asked, how can you pass different inputs? Here we have the kernel. On the right you see 3 different branches, and on the left you see 5 different configuration ways to run, and then you can see that there are some failures, for example, here. And then it's a pretty long report. Here it takes DPDK, which is like an Intel toolkit, and runs it against 6 different versions of it for all of these branches, and tries to report if it succeeded or not, and so on. So yeah, that's kind of a nice thing. You can tweak one input and get a new package with just that difference, and so on. Any more questions? All right. Well, if you want to know more, there is a repository on our GitHub IOHK ops, but it's just to get a feeling for the language, where to start. Go to GitHub, and here you have like links for manual. One of the things I have to warn you, it's quite a big ecosystem, so you have to play it kind of smart. I recommend starting with the language itself and just go to the chapter. What's really nice is the Nix spills. It's like, I don't know how much 19, 19 sections that goes like through what I covered right now into detail, and it like teaches you the language, and then goes into more like how do you build software, and even about Docker, and teaches you the concepts in X and so on. So it's a pretty like throughout tutorial. I highly recommend starting here, but it takes a while to go through. Yeah, Alex, you ready? All right, thanks.
Okay. Thank you. Yeah, it happened again, so I'm not sure. Yeah. If it's not possible, I can just use another OS. Let me just try it. Okay. Thank you. No, I'll just... you'll it's permanent this time. All right, so I'm going to be talking about Haskell, Hashmaps, and QuickCheck. So when we're using Haskell and we want to use structures to hold the data, the most common alternative is the containers package. It's general purpose, it's really efficient because it relies on ordering, and it offers an implementation for maps, for sets, and that's mostly what we use it for. There are other structures in it, but they're not really that commonly used. And as an alternative, we also have unordered containers, which instead of being structures that are based on order, they're based on hashing. So they're an alternative that we use when, for example, we don't have a notion of ordering for the data type that we're using at the moment. So a hash map's internal structure, it's not to get too technical, but it's a hash array map trie. So if you know what a trie is, this should look familiar to you. And what happens is that essentially it's a k array tree where k is 16, but it's not always 16. It can hold at most 16 elements at each level of the tree, but it doesn't have to be 16. As the tree itself grows, it adjusts automatically. So and this array is in Haskell we also have arrays we have to have, and it's not the one that other commonly used packages export. It's something else that is a GHC primitive that is used for performance. So the problem that I was solving at IOHK was that it's not really a problem, but I noticed that, for example, in the containers package, when you want to know the size of a container, a map or a set, it runs in constant time. It's just a check because there's a field in the map or set structure that says, okay, here's the map or set's current size. With hash maps, that's not the case, at least not right now. What happens is that if you want to know the size of a hash map, you have to actually traverse the entire structure, which is not terrible. It's not something that causes code to run much slower, but it's not ideal. Ideally, we would just query some field of the structure or perform some very fast operation that runs in constant time, and we get the structure size. The solution I came up with the help of my coworkers, of course, is we basically perform some renaming, and then our new hash map becomes the old hash map plus a size value. And this size becomes it starts to represent the size of the tree structure that's inside the hash map. So what happens is that every function that may modify a hash map size now has the responsibility to update that size in the process. And accordingly, every function that does not modify a hash map size cannot do that, or at least should not do that. To give you one example, this isn't the whole function because it's really, these functions are really long because they use a lot of Haskell tricks to make things run fast. But basically, when we want to insert an element into a hash map, we have pattern matching, which is something you're all familiar with. So I just pasted the first example, the first couple examples, and there's some spaces missing there, but that's fine. That, for example, when we want to insert an element into an empty tree, we just do what we're supposed to do. And this becomes a little different because the insert function now calls an internal function that's not exposed to the public API. And this internal function has the responsibility of returning not a tree, as the old helper function Go did, but it returns a tuple. Size is just a tuple in the Haskell way to make things fast. It's not an actual tuple because they're just they're not very efficient. It's a tuple that has a size and a tree. So what happens is that every function that modifies the hash map size returns a tuple. that says, first, here's the difference or increase or decrease, it depends on the function, in the hash map size. And this hash map is the one that I'm returning to you. So, for example, when we insert an element into an empty tree, what happens is that we return sized, and then 1, because the original tree was empty. The new tree is a leaf, so 1 element. So the number of elements that we added is 1. And we do this throughout. And as an example of an operator that does not change the hash map size, we have adjust. Adjust is simply supposed to, it has a function from v to v, v is value, and a key and a hash map. And if this key is present in the hash map, we apply the function to this, the keys of the value. If it is not present, we don't do anything. So previously this function was, again, I'm not going to paste the function because it's really quite long. But now, since the function isn't supposed to change the hash map size, we just keep the previous hash map, which is SZ there. And then we return the new hash map, which is the result of applying the helper function, because all of these functions have helpers because of the underlying structure of the hash map. The functions that operate on it are a bit complex, so the package is structured in a way such that internal functions are usually, there's more than one, and they're almost always called Go, which is a standard in Haskell, more or less. So because of these changes, because of the fact that now every hash map has a size field that the functions have the responsibility to update, we can just write size is the size field inside the hash map. And this is constant time, which is an improvement. And doing this actually helps in other ways than making calculating hash map size fast, because, as an example, when you compare two hash maps, which is not very common, but for some reason you might have to do that, two hash maps are only the same if they contain the same elements, if and only if. So what happens is that if they have a different number of elements, they can't be the same hash maps. So the previous code that, again, uses helper function to traverse the tree and compare the two hash maps can now simply compare the sizes there, S1 equals S2. And then because Haskell has lazy evaluation semantics, what happens is that if S1 is not S2, is not equal to S2, it doesn't even bother going to the helper function, which would traverse the two maps in linear time. And instead, it just performs a simple comparison, which is constant, and we have I would say, a significant improvement. Another example in this package is the intersection function, because the intersection function uses fold_L with key. A fold_L, I'm sure that you all know what a fold is. A fold_L with its key for hash maps, and the apostrophe means it's strict, because when we want to write fast code with Haskell, we can't really rely on, or all the time, on lazy evaluation, because it's sometimes a good way to leak memory. If you want speed, you have to be strict almost every time. So a fold leaks memory if it's not strict. So the intersection function uses it to traverse the second map, and then it basically just looks up the keys of the second map in the first map, and then it's just I put the comment there so you could see it. Intersection of two maps returns elements of the first map for keys existing in the second. But the problem with this is, if the longer hash map is passed as the second argument, it's going to have to traverse the longer hash map, which means more lookups and more insertions, which in the end means a larger time spent performing these operations. So with this improvement, we can just see, because calculating the size takes constant time, it's not really a problem. We can just compare. If the first hash map is smaller, then we pass it as the hash map we're going to traverse. If it isn't, we use the other one, which means that in this case, we have a different helper for each case, which traverses the respective hash map and saves some time. And we can do the same for the union function and other related methods, because when you traverse the hash map to perform such an operation, and you look up and insert things, it's usually an improvement when you do it the least number of times. So problems with this approach. Functions that may alter the hash map size might not do it, or do it incorrectly. So what happens is that if we write improper code, or if we interpret incorrectly what happens to a hash map size in a certain operation, then the size function at some point in time after a certain operation might stop returning the correct value. And functions that shouldn't alter the hash map size might, because of again a bug, a typo, something unexpected, or a mismatch between the function specification and its actual behavior. And there's another problem, but this is more or less unrelated to this talk, which is there's a performance penalty for this, because having to take care of all this, so to speak, housekeeping, it takes time, it takes cycles, and although it's a constant number of, it's a constant penalty, it's always the same, the overhead adds up. So we have to find a way to make it fast enough so that the benefits from making size run in constant time have to outweigh the problems with all this overhead and upkeep. And this package is supposed to be fast. It's supposed to be something that we use when we want fast lookups, when we want performance, and any regression because of a pull request, which is what I did here, is something to be looked at seriously. So how do we solve the first two problems? The third problem is something else entirely. So functions on hash maps, or every function really in Haskell, have, not just Haskell, functions have properties that can be expressed logically. So for example, the insert function has a certain property that is, if a key is a member of after we insert a key in a hash map, and then we query that key for being a member of that hash map, the answer should always be true. And the reverse, if we delete the key and ask if it's a member of the hash map, the answer should be false or no. So in this case, the properties we're going to be interested in are about how the functions manipulate the hash map size. So in the case of insert, if the key is already part of the hash map, then the size should be the same as before the insertion. If it's not a member, then we should increase by 1. And a bit of a more, not really complicated, but slightly more complex example. The size of the union of two hash maps should be, and this is with some elementary set theory, should be the size of the first one plus the size of the second one minus the size of their intersection. So with these properties, since we have QuickCheck at our disposal, we can have property testing, which is a way of testing that these properties I just showed, and others, because I'm not going to show them all here, there are many, actually hold. So first, to get to the test started, we just have some type for keys and values. It doesn't matter which, because we want to know about the size, not what happens to the keys or values. So in the actual package, in the test suite, key is an integer that has a lot of collisions to generate interesting, so that there are actually collisions in the hash map. And the value is an int as well. And we write a small DSL for hash map actions. And this DSL is basically an expression of every single individual action that we can perform on a hash map. So insertion, deletion, union, intersection, filter, and there are plenty more. I think the actual data type has some 15 or 20 different cases. And just an aside, unfortunately, we could have function arguments, for example, to filter, so that when we wanted to create a random filtering action on a hash map, we would actually create a random function from bools to int. But that won't work very well, because in Haskell, you have to have arbitrary instances for the things you want to generate with QuickCheck, and we don't have a way of showing these the instances of functions that we generate. So in this case, we just pick something that works. For example, the function even from bool to int, which checks if a certain integer is even. And then we write the arbitrary instance for the hashmap action type. And what happens here is that we assign frequencies to certain actions, because it's not very interesting if at a certain point in time the hash map just becomes empty and we're just trying to delete things from an empty hash map. That's not very interesting. We want to see a sequence of actions that actually causes or may cause problems or bugs. So we assign higher probabilities to actions that increase the hash map size, and we assign lower probabilities to actions that decrease the hash map size. So deletion and okay, I made a small intersection shouldn't be higher than an intersection of two hash maps will never increase the size of the first hash map. So that's a small problem there. That's hypo. And then we have the state that we're going to use to start these tests. Tuple. It's basically our models, so to speak. It's the abstract representation of a hash map size during the execution of a hash map program, which is a sequence of those hash map actions that we saw before. So here we have basically the size of the hash map and the hash map itself. And what happens here is that the initial test state is 0 and empty, which is the neutral value of the hash map monoid. And we could just generate a random hash map, but it's it'll be simpler to find the cause of problems if we just start with an empty hash map. And then we increasingly apply actions to it. And how do we do that with this function? It's apply action to state, which is if you look at the type, it might look like something that we can use a fold on, which we will. And essentially, we have a hash map state or a test state and an action. And what we want to do is apply this action to the current hash map state and produce the new one with the updated state. So, for example, if the action is an insertion, then if the key that we generated is a part of the hash map already, then the state doesn't change. Because even though the hash map is updated, so as you can see, agem tick is actually agem insert, and then we insert the key into the value. We don't care, the size does not increase, but in the other case that the key is not already a part of the hash map, then we increase the size by 1. And then what happens is that we do this for every single action. For unions, deletions, intersections, and so on. So in the case of the union, we update the hash map state's size by doing the same thing that we saw in that property hash map size plus the size of the other hash map, and we subtract from that the size of their intersection. And the hash map from the state is also updated as well. It's missing the line that actually defines agem tick, but agem tick is no, it's actually there, which is this part here I was referring to. So, and for deletion and all the other actions, we do that, and it just goes on. So, and this is the actual test. So we generate a random sequence of actions, and then we have a property, which is with the property we actually want to test. That is size invariant. That the size actually, the size field in the hash map accurately portrays the size of that hash map. So essentially, I added some comments there because scanl might not be what it might have a different name in other languages, but scanl is basically applying fold incrementally. So if you have a list and you use scanl, you basically build the fold of the list with the given function, but incrementally, step by step. As you can see here in the comment, what happens is that it builds the fold from the beginning to the end, and then what happens is that the last element of the scanner is the fold. So we apply each action individually to the hashmap state, and we produce a list, which is the result of this action here. We produce no, not this one, this function here, and we produce a list that is whose head is the initial test state, and whose last element is the result of applying this sequence of actions here to the initial test state, and every other element is what's in between. And then the actual interesting part, which is we map this function here to the hashmap state, and then we check that the SZ is I'm using a syntax here, which is SZ. I'm not sure if you recall, but it was the field from the hashmap state type, and we check that SZ is actually equal to the size of a gem. A gem is the hash map. That's the second field of this type here. And this equality function here is specific to QuickCheck. It compares two numbers. And if they're not two numbers, it compares two values. And if they're not the same, it says, okay, here's the pair of values for which I failed, which is what we want. If it fails, it'll tell me, okay, this sequence of actions caused me to fail because the size was n, and I expected n plus 1, for example. I can run some tests for you afterwards so you can take a look. And then we use conjoin. Conjoin is a function that, I have some notes here, takes a list of properties and gets its conjunction. So we don't just check that the final state is actually what we want. We check that every step of the way, the size that we got and the size that we expected are the same. And I could, this is a bit of a simple example, but if you look closely at the way that this function previously was organized, you might say that this is an automaton, and this here is our state transition function. So we could use more formal properties then to define this in a more elegant way, but to suit the purposes of my work, this was sufficient. So after all of this testing, what is it that we should do about the tests aren't perfect, and even QuickCheck with his it generates the values for tests, and it actually does all of that for you. It can't possibly cover the entire state space. So instead of using tests to maybe have some sort of assurance that things work, we can have more rigor and formality by using a tool like Liquid Haskell. I'm not sure if any of you here know what Liquid Haskell is. You do? Okay. So Liquid Haskell is a way of actually encoding some assertions about the code that we're running as comments. I'll give you a quick example here. So this is a work in progress, but what happens is that this is the same code of the as before. This is the insert function, and this signature that I've highlighted is Liquid Haskell. It's a comment, as you can see here, because this is the Haskell syntax for comments. And what happens is that Liquid Haskell is a tool that uses SMT solvers to verify whatever assertions its user passes to it. So in this case, I use Liquid Haskell to augment the regular signature for insert, which is here, with some assertions, which are, in this case, that the result type, after I take a key, a value, and a hash map, the result type is the set of hash maps. This syntax is closely related to set theory, that the resulting type of hash maps is the type such that if the key that we want to insert in the argument hash map is already a member of it, then the size of the type of hash map should be the same as the input hash map. Otherwise, it should be incremented by 1. And this is the property that I showed you before. That's about the insert function. So instead of testing these things and maybe catching a failing test case, we actually encode these properties as logical propositions, and we test them, not test them, but we run them using an SMT solver, and Liquid Haskell will tell you, okay, this is in fact true of all hash maps. But unfortunately, I don't have anything to show you about Liquid Haskell right now, because it's still, as I said, a work in progress. And not only that, Liquid Haskell is still, I would say it's much more mature than the first time I used it, which was in October 2017. But it's still a little difficult to use. So perhaps one future meetup after I get this to work, I'll make a presentation that instead of being about QuickCheck, it'll be about more formal assurances using Liquid Haskell. So before I end my talk, I would like to show you some examples, such as, let's see. So this here is the base module for the Hashmap package. And what I wanted to show you was something that actually happened when I was doing this pull request. This is the union function. It's not the union function, it's an internal function, but to keep things simple, it's the union function. And what happens when in a certain pattern match here, to keep things simple, I'll just say that we basically, the size that we have to, okay, I'll just scroll up a bit. The size that we're going to return in the sized pair is a result of in the union function. Basically, what happens is that the size that we count in the insertion function, the size returned was if it increased, if the hash map increased in size or not. What happens in the union function is that the size counts down from the second hash map size. This is a trick that I had to come up with because actually making sure that the union function returned the increase or the difference in the first hash map size was quite difficult, so I had to figure something out. And what happens is that just even if you are not quite sure what is going on here, I wasn't sure at the beginning either. I forgot to put this to subtract 1, and then a bit shortly afterwards, I finished the PR. I decided to write this test suite, and what it actually found a problem, and it gave me a precise sequence of actions that triggered it. So I'm just building the project here. So I was it was during development. I simply forgot to write -1 here, and what ultimately this means is that when you perform the union of two hash maps, the size is going to be 1 unit off. So after I ran these tests, it'll take a while because Haskell is famously known for its long compile times, longer at each year. So here it is. What happens is that the size property failed, and it then produces a minimal list that triggers said failure. So what happens is that QuickCheck generated an action, a hash map action, that is a union of a hash map, and then another union here. So because QuickCheck returns these two actions here, which is the first union here, and this the first here and the second where I just showed you, the first one probably works just fine because the initial test state is empty. But after the second union, because of the -1 I write here, there's a mismatch. So 32 is not 35. And it tells me why by presenting me with this list of actions. So this actually happened, and not just in a single place, because I wrote this code over the course of 2 months, and so I kept forgetting things. We're all human here. We make this sort of mistakes. But QuickCheck helps us by showing us, by generating complicated test cases and showing us where they fail, or and if they do, why. So that's it for my meetup, for my talk. And I'd like to thank Sarah Kill and IOHK, which to whom I'm very thankful, because I got to spend the better part of a trimester working on this and this alone. And I'd like to thank the group as well for letting me host this talk. And that's it for me. And in case you're wondering, I actually use this approach in the development of Cardano SL as well, to test a couple of systems by generating a random sequence of actions and then checking whether or not the system, the protocol actually behaves properly. So it's not a very complex set of tests, but it's helpful. This I forgot to mention, but in Cardano we use this package. So it's not yet a part of Cardano because I haven't merged this, or not me, but the maintainer hasn't merged this PR, because I should reconnect this, but because I actually had some performance numbers to show you, but let's see. Domen, if you may. I should have done that. Okay, cool. Thank you again. So these are the performance numbers that I pasted, because the maintainer has been a bit busy with other things, but he's been back to take a look at my PR now. So as soon as the pull request is actually merged, which it should be, just give me a second. Here it is. It's been it's an ongoing discussion. I made the PR in October, and it's still open, so it might take a while more until it's actually working. But yes, it'll be used in Cardano because, as I said before, when we need to use structures in Haskell, we either use containers or unordered containers. There are a lot more options, but for the most general use cases, these two packages are sufficient. So, yeah, to answer your question, yes, Cardano uses, or if I'm hopeful, it will use these changes, yes. Oh, the benchmarking. On the left, we have my the benchmark of the code from my PR. There's a comment here, but it's not very clear. And on the right, we have the current, the performance of the current package that's available via Haskell's dependency managers. So it's more or less the same, but there's a slight problem with filtering functions, because they're about 5 times slower, which is not good. And I'm pretty sure this is something that I'll have to look into with more detail, because Haskell is like this. The filter function doesn't even do anything special with the size, but it's 5 times slower. That means I have to throw in some low-level magic to make it work. So yes, but uh, in in in, ge- in general, it's not more than 10% slower in overhead, and aside from those exceptions, it's usually the same performance. Yeah, of course, yes. So it's not this one because the maintainer asked that I write a different set of benchmarks for size. So here it is, and the size of the benchmark hash maps is not more than I think it's 2 to the power of 12, which is about 4,000 elements, and it's it's fast. It's about 7 nanoseconds in the version that I wrote, and a few thousand times more in the current version. So that's to be expected because it goes from um it went to constant time from linear. So this is to be expected. Oh, that's a good question, a very good question. But this size function, the one that I changed, is for hash maps. And what happens is that let's open Emacs here. And what happens is that when you have an array, this module is not publicly visible. And this array type is this array hash. This is a set of GHC primitives. It's you can't see the source code for that. You have to. These are implemented as primops, which are primitive operations, which is not Haskell anymore. It's more low level to be fast. But when you want to know the size of this array, you use this function here. So this is the length for arrays, and these arrays are used inside hash maps. They're not really the same. But yes, you are correct in the sense that when we want to know the length of an array inside a hash map, we have to be careful so that we don't have any out of bounds. Yes. I'm sorry. What? I'm not sure because I asked one of the people that actually wrote this primitive function here, and it's constant and cheap, meaning quick. But uh, I'm sorry. Yeah, yes, it is in constant time. Yes, it is. It is. The functional length, either in the case of my code or the current code, for arrays, it's already constant time, which is this prim up here, size of array. But when you want to know the size of an actual hash map, because these arrays, the user, when they use hash maps, they don't know these arrays are here. Because this was a change that the maintainer made a few years ago. Because previously, a hash map was based on Patricia trees, if I recall correctly, which do not use arrays. And at the time, a user did not know that you could, whether or not you had arrays or trees or what other structure was underlying the code. What happens now is that the hash map is, I'll show you here. This is the same code that I showed you. A hash map used to be just this. So the user does not have any knowledge that it uses arrays internally. So the only size function that they have access to is this one here, which this is my the branch I'm working on. But the size function for hash maps has to traverse the entire structure, and there is no other way around that. No, in the unordered containers. In the containers, library, it's actually in constant time. So if you, it shouldn't take too long. Haskell containers. So I'll show you the source code really quickly. So data, and this is the other package. It's containers. It has maps and the sets. So for map, let's see, strict, internal. It's not here. So it's not here either. It's an internal. Yes, we have a lot of those because the release cycle in GHC, we have to keep things deprecated for several releases until people don't need them anymore. So let's see if I can find that. Unfortunately, searching doesn't work the way I expected it to, because the type signature is probably in different lines. So let's see. If I recall correctly, it was. See if I find it. Alright, doesn't seem to be here. Well, okay, I can't find it here, but let's see. Okay, I can't seem to find it. It's been a while since I've browsed the source code for this package, but yes, in the containers package, both for sets and the regular maps, what happens is that the size function is constant. Yes. Size. It's actually called size. Size, length. It's more or less the same. Okay, here it is for a set. So for a set, we simply just there's a field in the tree because sets internally are trees in Haskell, or in this package at least. We just query this field and we have it immediately. So it's a constant time. It's not until the PR is merged, if it is merged. Yes? The current size function. Oh, you mean I think I understand what you're talking about. Let's just take a look at that. Test size. So the property should be around here. Yes, you mean here, right? Instead of using since this is the branch I'm working on, this size function is the new one. So you mean instead of using this one, you mean using the previous one. That's because I assume here that the tracking that I do in this function here, for example, in the code I showed you, for example, for union, when the hash map states new size becomes this value and this value is this, it's because I assume that this value from where is it? That this field from hashmap state accurately represents the size of this hash map. So of course, if this function has a bug or an incorrect, if it has incorrect information, then yes, it's a problem. So I could have defined a size, for example, which is a very good idea. I could have defined in the old module, I could just define size tick, and then say and then define it as the previous size function, and then export this one only for tests and use it only. Where is it? Instead of doing all this, I could use the old size function as well. Yes, but I prefer this approach because in the end I ended up learning a lot more things, so it was more interesting to me. Yes. Oh, you mean the in the slides? Okay. You mean this? Oh, you mean the actual test? You mean in the slides or in the actual code? Okay, the actual code. So you mean okay, okay. Oh, yes, yes, yes. Uh, you mean each of these case patterns? Yes, yes, yes. Because one other point that I can add to that is that even though this package is already a few years old and it's battle tested, so to speak, I did not want to rely on old code to test the new one. So I would rather do this than use the old function. It's not incorrect. It's been used 100, perhaps millions of times at this point. But I would rather write new code than okay, I'm not saying that new code is always better, but I would rather write the test itself here, so it's actually clear my intent. So it's clear that my intent here is that I have an idea of what each of these hash map actions, as I said, the type is quite big, that each of these actions does what is expected of it. So in this case, deletes or decreases the size of the hash map if the element is there, and so on. So yes. Well, there are quite a few modules for testing here. There are 6, aside from the one I wrote, which is this one. And there was let's see, hash map properties, if I recall correctly, it was yes, this one. So in this module, which was I didn't write this one. It's a previous module from someone that contributed to the package before I did. They have it's more or less the same idea, basically. It's equivalent. Not sure where it is. Model. Yes, they have a model which is the specification they're testing against. So in this case, they're treating an abstract hash map as the map from the containers package. And in this case, the property that they have is that yes, that for every list of key value pairs, in this case, as I said previously, the key is an int, which is a new type. It's hidden up there, and the value is an int as well. That the size of our model is actually the same as the size of our current implementation. So these two tests do more or less the same thing. This test and this test as well, but in slightly different ways. So for example, this test would not reveal to me a sequence of actions for which the size is different. It would only tell me, okay, here's this list of key value pairs, and size fails for it. And as I showed you before, when we have these two actions in sequence, this test would not actually catch this bug. Because as you can see, I said before that there were 6 test modules, and all of them except the one I wrote passed. So I'm not saying that, I could have just extended the previous module. I'm not saying the previous module was bad. I'm just saying that the test that I introduced actually catches these more tricky problems with the code. Yes, yes, yes. Because in practice, this is basically a single. We can think of this as a. Now I'm going into not quite a unit test, because this actually generates a different hash map each time it's ran, which is I would say more than the traditional unit test does. But it's basically a single. We're not testing different actions here. If you want to think of this hash map as a sequence of actions, we can think of it as, for example, a union of the hash map that this list represents and the empty hash map. While the test that we have now actually does not just a sequence of a single union, but 2, 3, 5, 10, however many QuickCheck actually decides to run. So I would say that the test that that is currently in this module extends on the behavior of this test here. So I would also like to add that while QuickCheck is actually an excellent tool that is still truly useful and remarkable in its ability to stay important and relevant, in Haskell especially, we've started to there have been a few other packages that implement the same behavior, but as is the case here, extend QuickCheck's functionality with more ideas. And one of them that I would like to comment on quickly is Hedgehog. And I previously said, not this one. I previously said before that this test could be looked at as an automaton, and that wasn't for no reason. It's because with Hedgehog, we can have abstract state machine testing, and this is basically a complicated way of saying that we can have tests like this one, but instead of actually having to write all of this ourselves and having to write an actual fold or a scanl, Hedgehog does all of that for us, and all we have to do is specify what the automaton is, which is, for example, the transition function, which is implemented here, and it'll do everything else. So with QuickCheck, there's an alternative which I haven't used before. I was planning on doing that for this talk, but I decided against it because it seemed a bit a little like overkill. But there's QuickCheck. I think it was state machine. Yes. So it's also state machine based testing with QuickCheck. So if you have a problem that is more or less equivalent to this one, and it doesn't lend itself very well to this sort of simplistic approach, then there are packages at this moment that can improve upon what QuickCheck would do for you. Yes. You don't. And that's why I wanted to use Liquid Haskell, because as I said before in the slides, QuickCheck is a great tool, but it's not perfect, because when the state space is too large, it's not actually possible to, or not feasible, to generate every single possible state and test it. Because in the case of Hashmaps, the maximum possible size for a hash map is the, well, however many integers that there can exist, and then the keys and values can be also different as well, so it's not feasible at all. So you don't really have any guarantees that you've checked every single possible value. What QuickCheck does is it generates the more complicated edge cases that programmers, human programmers, tend to miss. For example, the test case that it showed me here, which a human could possibly manage to replicate, but at a great cost. It would take a lot of time, mental effort, and what happens is that QuickCheck makes all of that easy for you. But the bottom line is, in answer to your question, QuickCheck does not generate every single possible value if the state space, in this case hash maps or integers or strings, is too large. Well, to be fair with you, I'm not really sure what unit tests are supposed to be, because there isn't really an exact definition, and they mean a lot of different things in a lot of different domains. But if by unit test you mean the simple contained test, then yes. For example, it is possible to make more complex tests, but I think this is sufficient for to have quite a high level of assurance that, not absolute, but a high level of assurance that the change I made to the size function actually works properly. Liquid Haskell, yes. As soon as I make it work, yes, it is. Yes, it uses an inference engine that uses underneath it an SMT solver, and in Liquid Haskell's case, it's Z3, if I recall correctly. So, well, let's see. I want GitHub. No. Yes. Precisely. Precisely. It is. But I'm not currently at IOHK anymore, or Serica. But just before I left, plans were in motion to use Liquid Haskell in the most critical parts of the system. So I'm not sure, because as I said before, this tool is really good at the moment, but it's still immature. And making it work in a production grade project like Cardano is not going to be easy, especially because Cardano is as one of the first, or one of the, well, it's a significant Haskell project in industry, and it's not going to be easy to actually make it work because the code is non-trivial, and Liquid Haskell might, there might be some unforeseen obstacles in using Liquid Haskell to cover the Cardano code base, but I think it is possible. So in answering to your first question, to verify a single file, you just run liquid, and to run the verifier in a project, all you have to do is run liquid as well, but with a few additional arguments to specify. Well, without code here, it's a little complicated just to stock, but all you have to do is use liquid, and that's it. And then it shows you, there's an example here, if I recall correctly, of the output. Let's see. Okay, it's not here. But it works in phases. First, it extracts the Liquid Haskell code that you wrote, and then it processes it, and then there's a pipeline of different steps, and it tells you on the command line, and then in the end, it outputs safe or unsafe. And if it is unsafe, well, let's see if there's an example here. No, there isn't. But if it outputs unsafe, then it'll tell you, okay, this module is unsafe, because in this module there was a function that was unsafe, and this is why it is unsafe. I I should really try to find an example because it's easier when you see it. So let's see. All right. I think they recently refactored the tutorial because the last time I used this was shortly before the last summer. But the tutorial and the introduction materials to the tool are excellent. And there's actually a Slack for the tool, a Slack channel, a group that you can join and ask questions in. And people are the people that actually wrote Liquid Haskell are there, and they're very helpful with everything. So if you have a problem, if you want to know where to go to learn how to use the tool, or for any other purpose, it's a good idea to ask the people who wrote it what you can do with it and how. So, but the tutorial here is a good start. Yes, yes. So if the module is unsafe, it fails at compile time, and you have a chance to fix it before it's actually in production live. So yes. Yes, but the compilation is a bit of a problem because it takes some time. All right.
1, 2, 3. So thank you very much to Bright Pixel again for hosting the meetup. It was like